Here at the beginning of the course, it's important that we get some basic research terminology out of the way so that we're all on the same page as we proceed through the course together. So first of all, we need to understand that when we say the word statistics, what we mean is statistical procedures. Statistical procedures are mathematical operations that are run in order to conclude certain information about the data. You use statistics to organize and summarize information and to determine exactly what conclusions are justified based on the results that were obtained. Those two bullet points that I just read are different types of statistics. I will describe the names of these different types of statistics in just a minute, but it's important that we understand that the two different types of statistics have different goals. But the goals of statistical procedures are generally to accurately and meaningfully allow you to interpret the data and to provide standardized evaluation procedures so that whoever runs the statistics, regardless of what school they attend or what profession they're working in, that those statistical procedures are standardized, and if anybody in the whole world were to repeat them using the same processes, that they would come to the same conclusions. It's another term that we need to understand here at the beginning of the course is populations and its counterpart, samples. A population is the set of all the individuals of interest in a particular study. Populations vary in size, but they're usually quite large. An example of the population might be like all the people in the United States. In fact, every 10 years we engage in the decennial census, and that census has the goal of measuring a selected set of questions for every single person living in the United States. That series of questions is very, very, very expensive for us to get. It costs billions of dollars in order for us to acquire the answers to those questions from every single person in the population. It's also somewhat inaccurate because even though an effort is made to collect the information from all the people in the whole United States, we still underrepresent certain people who live in gated communities or who are homeless, or other kinds of groups of people are underrepresented in the census. For that reason, it's usually just as effective to draw a representative sample of individuals. A sample being a set of individuals that were selected from the population, and they're usually intended to represent the population in a research study. So if you wanted to understand all Americans, instead of measuring all Americans, you could just take a random sample of Americans and ask them those 10 questions, and then conclude about the general population that they're pretty similar to the people that you selected in your sample. Now, we're going to touch on this more in future modules, but it's important that we emphasize again that this sample has to be representative in order for us to draw that conclusion, that that sample represents the population. This is a schematic of how the relationship between populations and samples typically works. The population is, again, all the individuals of interest. A sample is selected from the population, and we do some kind of research study with those individuals. We run some statistics on the individuals, and the results from the sample are then generalized back to the population so that we understand who these people are without having to measure all of them on whatever characteristic we're interested in. Some additional terms we need to know are variables and data. A variable is a characteristic or a condition that changes across people or has different values for different individuals. It's pretty intuitively named if you think about it. A variable is called that because it varies, or it is variable across people. An example of this might be height. Height is different across people. It's variable across people. Another example would be weight, or intelligence, or happiness. All of these things vary across people. Another term we need to know is data. Measurements or observations of a variable are known as data. This is probably a word that you're already familiar with, though you may not know that data is actually a plural word. The singular of data is datum, D-A-T-U-M, datum. So when we say data, we're actually describing multiple numbers. And if you are confused by the plural use of the word data, then you can just generally refer to it as a data set, which is a collection of measurements or observations. This is often organized in a spreadsheet like in Excel, and the data set will have multiple variables and multiple data points for each of many people in a research study. And so that will be collected in rows and columns and is known as a data set. Some additional words we need to know are parameter and statistic. Now remember before we talked about populations and samples? Parameters and statistics match those two groups one-to-one. So a parameter is a value, usually a numerical value, that describes a population. It's derived from measurements of the individuals in the population. So, like when we have the census, any number that we compute from the census is a parameter. That's a value that describes the entire group of people that we're interested in. A statistic is a value, again, usually numeric, but it describes a sample rather than the whole population. This is derived from measurements that we make in the individuals that are just in the sample. But the goal of statistic is to draw a conclusion about a parameter. So we don't usually know the parameter. Usually, it's too difficult to measure everybody in the population, so we don't know the parameter. But we do know statistics because we measure the individuals in our sample, and we're trying to guess what the parameter might be based on the statistics of our sample. So statistics are what we do know. Parameters are usually estimated or guessed at based on the statistics. Now remember, earlier I hinted that there were a couple of different kinds of statistics. Here's where I define the terms descriptive and inferential. Descriptive statistics summarize data, they organize data, simplify data. You are probably already familiar with these kinds of statistics. If you have lived more than a minute and a half in your life, you have probably seen tables, graphs, and averages. Inferential statistics, on the other hand, are statistics that are drawn from samples, and we're trying to generalize information from the samples about the population. They're used to interpret experimental data. Common terminology associated with inferential statistics are things like margin of error or statistically significant. I don't know if you've heard those terms before, but you're going to hear them a lot during this course. This course is primarily focused on inferential statistics. You're going to be learning how we can take a sample from the population, run some pretty complex inferential statistical procedures on that sample, and make a conclusion about a much larger group of individuals, the population, and trust that the conclusion we're drawing is probably accurate, within some margin of error, or within some reasonable degree of accuracy. We're next going to talk about statistics in research. The role of statistics in experimental research is articulated in this schematic here. If you had a population of college students, say this was a population of students just attending one school that you were interested in. Let's just, since we're attending Central Washington University, we'll go with that. If you were to take the students at Central Washington University and draw a sample of just 15 students and have them read from printed pages, and have another group of 15 students, another sample, read from a computer screen, this would be a typical experiment. You would then run some descriptive statistics that organize and simplify these groups of data. If you just glance at this right here, it doesn't allow you very well to see what's going on. You don't know what a typical student scores on an exam based on just having read the pages. And you don't know if people who read it from a computer screen did better or worse on the exam after having read on the computer screen. But if you take the average score of the students in sample A and the average score of students in sample B, you can see how they compare. If you use some graphs here to show how many people scored each score, then you can see some additional information about like the spread and the shape of the distribution. Those descriptive statistics are very helpful, but we still don't really know much about the whole population of college students just based on these two samples. The inferential statistics that I mentioned before will allow you to interpret the results. The sample data show that there's a 4-point difference between the two methods of studying. The people who read from printed pages scored about 4 points higher than those people who read from a computer screen. However, there's two ways we could interpret the results. One way is that there actually is no difference between the two studying methods, and the sample difference is just due to chance. It's called sampling error, and we'll come back to that concept in a while, but basically it's just luck, bad luck, that we got two groups of people that happen to be different, but it's not really because of the computer screen versus the printed pages, it's just random chance. But the second way that we could interpret these results is that there really is a difference between the two methods, and the sample data accurately reflect this difference. So the difference between people who read from printed pages and those who read from a computer screen actually is about 4 points different. It might not be exactly 4 points, but it's something close to 4 points different. And this difference in our samples reflects a real difference in the population of college students. And the goal of inferential statistics is to help researchers decide between those two possible interpretations, so we can know with relative confidence if there really is no difference or if there really is a difference. On the last slide, I described this concept very briefly. That's called sampling error. Sampling error is the idea that a sample is never identical to the population. If I draw a sample from the population and I compute some statistic from it, the actual population parameter, the value of that variable in the population, is almost never going to be the exact same value as what my sample showed. And that difference, that discrepancy, or the amount of error in our computation that exists between the sample statistic and the corresponding population parameter is called a sampling error. This isn't really being wrong, because it's way better than just like a random guess. If you were just to make just a stab in the dark about how much the typical male in the United States weighs, you probably wouldn't be very accurate. But if you took a random sample of people in the United States and measured their actual weight, you wouldn't be exactly right about the real weight of all the people in the whole United States if you magically could know all of their weights, or if you somehow had the means financially and logistically to bring all of them into a laboratory and weigh every single one of them and compute the average of all of them. It wouldn't, like, your sample wouldn't reflect the population perfectly, but it would be way better than a random guess. Anyway, again, the difference is between the sample statistic and the population parameter, that's known as sampling error. So an example of this is the margin of error in polls. You might have heard before something like, this poll was taken from a sample of registered voters and has a margin of error of plus or minus 4 percentage points. What that's reflecting is the fact that we know when we did this poll that what all the voters in the whole United States really feel about this issue is not going to be accurately reflected perfectly in our little poll. It might be a little higher or a little lower, probably something like up to 4 percentage points higher or 4 percentage points lower, but it's probably very close to what we estimate it to be. Like if you say X% of people are in favor of abortion, you might not be exactly accurate, but probably it's going to be within about 4 points higher or lower than that value. And that is reflecting of sampling error. Here's a schematic representing the concept of sampling error. If you took a population of 1,000 college students, say that was the entire student body of a college somewhere down the road, and you were to compute the population parameters for all the students together who attend that university, their average age might be 21.3 years old, their average IQ might be 112.5, and they might be 65% female. Now, if you were to draw two samples from that population, the statistics that you're computing from those samples are not going to reflect perfectly what these parameters really are. For instance, if you drew a sample of 5 people, Eric, Jessica, Laura, Karen, and Brian, their average age, 19.8, is not the same as the actual age of all the students together, 21.3. But it's pretty close. And it's expected to be close because these students represent, even though it's a small group, they represent the whole body, the whole population of all the college students who attend that college. Similarly, their average IQ and the percent female, it's not going to be representative of the whole population, but it's going to be close. The difference between 19.8 and 21.3, that's known as sampling error. And the difference between the average IQ of this sample and the average IQ of the actual population, that's again sampling error. That difference is sampling error. If you drew a different sample, just Tom, Kristen, Sarah, Andrew, and John, and you computed their average age and their IQ and their percent female, again, it's not going to be exactly accurate to the population, but it's going to be close. And the difference between these scores and those scores is sampling error. The next thing we need to talk about is that there are two different data structures. There's different types of experiments or studies that we run. And the two main ways to perform research are in data structure 1, a correlational type of study, and data structure 2, some kind of group comparison. Within the field of sociology, you're going to see that most studies are correlational, whereas within the field of psychology, most studies are group comparisons. So different fields or different disciplines will employ different types of research primarily, though there, no discipline is completely entirely fixed with one type of research, but you will see that some fields will use one more than the other. I'm first going to describe data structure 1. This is the correlational method. In the data structure 1, you take a group of participants and you measure 2 variables for each participant. The goal is to describe the type and magnitude of the relationship. Patterns in the data reveal relationships that exist between those 2 variables, and this is a non-experimental method of study. Let me give you an example. This study here measures wake-up time and academic performance for a set of students. If you look at the overall trend of these data, it appears that the later in the day you wake up, the worse you do academically. So as your wake-up time increases, your academic performance decreases. But you can see each individual is plotted on this scatter plot. Like student A wakes up at 11 a.m. and their academic performance is 2.4. So you could plot them here. 11 is their wake-up time, and 2.4 is their GPA. That dot represents student A. And each of the students, A through H, are represented in this scatter plot. Notice what we didn't do here. We didn't tell them what time to wake up. We didn't force them to do anything. We just measured 2 variables in this one group of students. Again, this is a correlational design. There are some limitations with the correlational design. They can demonstrate the existence of a relationship, but they don't provide any kind of explanation for why that relationship might exist. And most importantly, this kind of study cannot demonstrate a cause and effect relationship between the 2 variables. You've undoubtedly heard before this phrase, correlation does not mean causation. So indeed, when you do a correlational study, you can't know for sure that the one variable is causing the other. So here's an example. A researcher finds that children in the local school who regularly eat a nutritious breakfast have higher grades than students who do not eat a nutritious breakfast. Does that mean that a nutritious breakfast causes higher grades? Well, almost certainly not. You can imagine that if you wanted to get better grades, the first thing you should do is probably not just wake up and eat a breakfast. You should probably study hard, and you should probably allocate resources to tutoring, and there's all kinds of things that are likely to cause higher grades. But eating a nutritious breakfast is likely correlated with other kinds of family dynamics that result in higher grades. Like, the kids who eat a nutritious breakfast probably have more present parents. They're probably wealthier than other students who don't eat a breakfast. They probably have a more structured routine at home where their parents expect them to go to bed at a certain time, wake up at a certain time. They plan ahead for breakfast to be had before they go to school. So there's all kinds of family dynamics that eating a nutritious breakfast seems to be correlated with, and those also happen to be the same kinds of things that help people get higher grades. So it's not that the nutritious breakfast causes higher grades, it's just that those things are correlated together. The next data structure that I wanted to talk about is comparing two or more groups of scores. In this kind of research, one variable defines the groups. Scores are then measured on a second variable. Some of this kind of research is experimental, but some of them can be non-experimental, and so just knowing that a study has employed this second data structure doesn't mean that we can infer causation. But some studies that employ this method can be used to infer causation. Let me give you an example of how these look. The structure of an experiment typically goes like this. You would have one variable that defines the groups and another variable that measures the scores in the groups. So variable 1 in this study is counting money or blank pieces of paper. That's the independent variable. So some people counted actual money, and some people had slips of paper that were the same size and shape as money, but they were actually just counting plain paper. And then when the researchers measured some variable, the variable that they measured was pain ratings. So they manipulated participants in this study by placing their arms in ice-cold water and asking them to rate how bad their pain was. But some people had counted money beforehand, and some people had counted paper beforehand. And those people who counted money, it seems like if you just glance at these scores, they had less pain than people who counted paper when they were placing their arms in ice water. Anyway, the point of this slide is to articulate that the structure of an experiment is generally to have one variable that defines the groups and the other variable that measures the outcomes. The goal of an experimental method is to demonstrate a cause and effect relationship. Experiments are one type of this second data structure. In order to have an experiment, you have to have two things. You have to have manipulation and control to rule out alternate explanations. So when you manipulate something in an experiment, you decide one of those variables, the grouping variable. So the experimenter will take people and assign them to one condition or another condition. The experimenter also has control over the influence of other kinds of variables that are going on in the lives of the participants. These include both participant variables and environmental variables. So a good experimenter will have a laboratory condition where all of the external factors are kept the same, so that every single person who enters the laboratory experiences that experiment in the exact same way as everybody else. Participant variables are more difficult to control, but if you randomly assign people, then you can average them out across groups. So even though we can't force people to have certain characteristics when they come into our experiments, if we randomly assign them to the conditions, then they end up averaging out and being approximately the same across groups. And that's a level of control that the experimenter also has. We need to know about these words in an experiment. An independent variable is the variable that is manipulated by the researcher. That's usually the grouping variable. It's called independent because no other variable in the study influences its value. It is independent of any other influence except the researcher. The researcher decides it. The dependent variable is the one that we observe to assess the effect of the treatment. It's called dependent because its value is thought to depend on the value of the independent variable. So the grouping variable, whatever the experimenter decided is going to be your condition, that's going to determine what happens to your outcomes. That's why we call it dependent, because it depends on which group you're in. It depends on your independent variable. So I'd like to take a moment here and practice identifying the independent variables and dependent variables in each of these 4 experiments that I've described here. As you'll see throughout the course, I have built in lots of practice exercises. When I teach this in person, I force my students to take a moment and work through it on their own, sometimes to discuss it with each other, with people that they're sitting next to. But being that this is an online class, I don't have that kind of control. So what I'd like you to do is pause the video for a moment and read through each of these and try to decide which is the independent and which is the dependent variable. If possible, please take out a piece of paper and just jot down your answers to these questions, because when we go through it together, I want you to be able to assess your own learning to see how well you understood the material and whether you need to really kind of work more on this or if you've mastered it and can move on. So please pause your video, work through this, and we'll assess in a second. A researcher wants to know if more at-risk high school seniors will graduate if they participate in an intensive study program than if they don't. So what's the independent variable here? The intensive study program. That's the thing that the researcher has control over, whether students do or don't participate. What happens because of that is the dependent variable. And in this case, that's whether students will graduate. Next one, a researcher wants to know how caffeine affects the growth rate of children. In this case, the independent variable is caffeine, and the dependent variable is growth rate. A researcher wants to know whether Americans hold more implicit racist opinions after Trump was elected than they did before. In this situation, the independent variable is Trump's election, and the dependent variable is implicit racist opinions. Fourth, a researcher wants to know if children have larger vocabularies when they are sent to private school. The independent variable here is being sent to a private school, and the dependent variable is the size of the students' vocabularies. Alright, moving along, I want to finally articulate just a few more aspects of this second data structure type. Remember, we're still talking about these data structures that have groups, and we're measuring variables within the groups. It's important that when you're running an experiment, that you have control over the situation. I hinted on this briefly before, but I want to articulate a little bit more about what I mean as it relates to control. There are a couple of methods of control. One way that you can control things is to randomly assign your subjects to conditions. I briefly described that before, that if you take people and you decide by, say, flip of the coin whether they're going to be in the counting money group or in the counting paper group, then you're going to average out the characteristics of the people so that you don't end up with a whole bunch of men in one group and a whole bunch of women in the other, or that you don't end up with a whole bunch of strong, tough people and a whole bunch of wusses in the other. You want two equivalent groups. One group equivalent to the other is going to count money, and the other group that is the same kind of people, the same equivalent group, is going to count paper. And when you have these two different groups do that thing, you can then conclude, because the groups are the same at the outset, that the differences you observe in the dependent variable, like pain, are caused by what you did to the two groups. There, in this example, it's caused by the fact that one group counted money and the other group counted paper. Another method of control is matching subjects. You can match subjects based on similar characteristics if you know the kinds of things that are likely to influence the dependent variable in your study. You would do this when you don't have control over random assignment, but you do have the ability to measure people on these characteristics and kind of match them up into two different groups. So you might say, like, in a naturalistic situation where you can't run a real experiment, you might say, I'm going to take a person who's a female, age 20, who has an IQ of 100, and I'm going to match her up with another person who's a female, age 20, and has an IQ also of about 100. And I'm going to create approximately equivalent groups. So that's not randomly assigning, but you are still creating two approximately equivalent groups by taking two similar people and putting them in two different groups. A third method of control is to hold the levels of some potentially influential variable constant. And we do this in a statistical fashion. So you might take like age or education levels and you put it in your statistic in a way that removes its influence from the numbers first, and then sees whether there's any effect of your experiment left over once you control for or hold that level constant. We also want to describe this control condition, this idea of a control condition. In an experiment, there always has to be some individuals who don't receive the experimental treatment. They either receive no treatment or they receive a neutral placebo treatment. And the reason why we do this is to provide a baseline for comparison with the experimental condition. The experimental condition is the opposite. These are the individuals who do receive the experimental treatment. And so at the end of the day, we have a group who got treated and a group who didn't get treated. In the example again of the paper and money, the experimental group would be those who counted the money. But in order to know whether counting money helps reduce pain, we have to have some other similar condition where the people didn't count money. But they have to do something similar, and so we have them count paper that's of a similar size, maybe a similar color. And by doing that, we are able to see these two groups did almost the exact same thing, but the only difference between them was that one of them counted money and the other one didn't. So the control condition is the people who counted paper. Sometimes we don't have the ability to manipulate what's going on. Like in real-life situations that are less experimental, where we can't evaluate something in a laboratory, we sometimes have to use non-experimental methods. In such situations, we have non-equivalent groups. The researcher will compare groups because they can't control who goes into which group. A classic example of this would be to compare men and women. We can't force a person to be a boy or a girl, but we can measure how boys and girls are different from each other on various characteristics. Another example would be pre-test, post-test. If individuals are measured at 2 points in time, a researcher can't control the influence of the passage of time, and you're not sure if the people got better just because time passed, or if it was because of the treatment that you inserted in between time 1 and time 2. In both of these situations, what we call the independent variable is actually a quasi-independent variable. Quasi meaning sort of. So it's not a true independent variable because it wasn't determined by the researcher. But we still sometimes call it an independent variable anyway, just because it's useful. It's just useful verbiage to be able to describe it in a way that sounds like it's an independent variable, even though it's technically quasi-independent. It's just kind of shorthand. Here's a couple of examples of non-experimental studies. Like I said before, you might take two groups of people that you couldn't randomly assign, that you couldn't decide which group they're going to be in, like boys and girls, and you might still measure the differences between them. In this example, you would have verbal test scores measured. And you would ask, are there any differences between the scores of the boys and the scores of the girls on this verbal test? And you couldn't conclude that it was necessarily because of being a boy or a girl that you scored better or worse, but you would be able to conclude that boys and girls are different. So again, you can't determine causation. In this second example, we have before therapy and after therapy. Now, we have depression scores measured in these two different groups, and we would ask, is there any difference? And if people got better after therapy, we couldn't necessarily say that it was because of the therapy that they got better, because some people might have just gotten better over time anyway. But we can say whether there is a difference between before and after therapy. Again, we cannot determine cause and effect. We're still working through vocabulary terms just to make sure we're all on the same page. And the next thing that we need to understand is the difference between constructs and operational definitions. Within a research realm, a construct is an internal attribute or some kind of characteristic that cannot be directly observed, but it is useful for describing and explaining behavior. So an example of this would be love. You can't directly measure love. Like, people don't have 14 pounds of love or 12 ounces of love. You can't measure it directly. You can't measure it in inches. You can't measure it in any kind of physical way. It's not directly observed. But there are so many strong pieces of evidence that suggest that one person loves another that you could create some kind of working definition. We call this an operational definition. And this identifies the set of operations that are required to measure an external or some kind of observable behavior. So even though we can't directly observe love, we can observe kissing, hugging, words of affection, note writing, flower buying. There's all kinds of things that we can measure. And if we were researchers and we wanted to try and find some method of measuring this idea, this construct of love, we could operationally define it in a way that was like number of kisses given. And that might not be a perfect definition, but it would, for the purposes of our particular study, be our working definition. We've chosen to define love as the number of kisses given. That's the operational definition. And this uses the resulting measurements as both a definition and a measurement of that hypothetical construct. So we've chosen to define love for the purposes of this study as number of kisses given. And that's both our method of measurement as well as our definition of love. The next set of terms that we need to become familiar with is discrete and continuous variables. The kind of statistic that you can use, the kind of statistic you can compute, will depend on the kind of variable you have. It's therefore very important that you understand as much as you can about the variable you've measured. Discrete variables have separate, indivisible categories. There's no values that can exist between two neighboring categories. Many of the independent variables that we have described so far fall in this discrete variable type. For instance, if you have categories of counting paper versus counting money, those are separate categories. There's nothing in between them. You can't split them. It's just separate categories. Being a boy or a girl, that's a discrete variable. A continuous variable has an infinite number of possible values between any two observed values. In other words, if you have a 1 and a 2, you can split the difference into any number of infinitely small sections or fractions between the two. Somebody could score 1.1276347 into an infinite number of decimal spaces. Every interval is divisible, like I said, into an infinite number of equal parts. It's these two types of variables play into a concept that's known as scales of measurement. So we can further break down these discrete variables and continuous variables into nominal, ordinal, interval, and ratio variables. This is one of the top 10 most important concepts that you will encounter in the study of statistics. It doesn't matter where you use statistics or where you study them. From here on out through the rest of your life, I guarantee you will hear these terms used again by other professors and other students. These are universally used terms, and it's very important that you understand them because, again, the statistics that you can compute will depend on which variables you have. So if you only have nominal variables, there are certain statistics you can't run. If you have only ratio variables, again, there's certain statistics you can't run, and there's certain ones that you can and should run. Okay, so now to describe these. A nominal variable is one that is a label and just a category. There's no quantitative distinctions. For instance, none are better or worse than any other within this, numerically better or worse within a nominal variable type. So some examples of this are gender, male and female. A diagnosis, you have cancer or you don't. You could be in the experimental or the control group. The list goes on and on. But any type of categorical variable is known as nominal. An ordinal variable is like a nominal variable in that it categorizes observations, but it's different in that it categorizes them in an ordered way. That's why it's called ordinal. They're organized by size or magnitude. Some examples would be like your rank in class. If you're a sophomore, if you're a freshman, sophomore, junior, senior, those are ranked in a particular order. Clothing sizes, a small, medium, large, and extra large. But very importantly, we need to understand here that the difference between a small and a medium is not necessarily the same difference as between a medium and a large, or a large and an extra large. Sometimes you'll see cup sizes in like in a restaurant, and a medium will be like 2 ounces bigger than a small, but a large might be 6 ounces bigger than a medium, and an extra large might be 20 ounces bigger than a large. But it's still called small, medium, large, and extra large. They're ordinally ranked, but they're not necessarily the same distance apart. Olympic medals are also an example of ordinal. You've got gold, silver, bronze. An interval variable is an ordered category, but it's one better than an ordinal variable because the intervals between the categories are of equal size. So some examples of this would be temperature, IQ, and golf scores. The difference between 12 degrees and 13 degrees in temperature is the same as the difference between 13 and 14, or 14 and 15. Each of those numbers is the same distance apart as all the other numbers. They are also ordinally ranked. Your scores get better or worse, higher or lower. But importantly, an interval variable has an arbitrary or absent 0 point. What that means is the 0 point on these scales is either made up or it doesn't really exist. I'll give you some examples. In the case of temperature, if you're using like the Fahrenheit scale, 0 degrees doesn't actually mean the absence of temperature. In fact, it just was arbitrarily chosen. It doesn't mean anything at all. In the Celsius scale, 0 degrees is something different than it is in Fahrenheit. In the Celsius scale, 0 degrees reflects the point at which water freezes. But that 0 point, again, doesn't mean the absence of temperature. It's not saying 0 of this thing. It's just an arbitrary point that somebody picked. IQ has an absent 0 point. I don't know if you know this. We'll talk about this several times throughout the course, but IQ scores have an average of 100. Most people score somewhere around 100. Some a little lower, some a little higher, but it's impossible to get an IQ of 0. Nobody can. Nobody does. In fact, the lowest score that you can expect to get on an IQ test and have it be a trustworthy result is about 55. You can score lower than on an IQ test, But when you score lower than that, nobody's really sure how to interpret it. The tests become very unreliable at that point. But most people will score somewhere between about 50 and 150. Nobody scores a 0. So this is an example of an interval scale, because you can score 1 point higher than the next person, or 2 points higher, and each point is the same distance apart, but there's no 0 point. Golf scores are another example, because you're really just scoring above or below par, and par is an arbitrary amount. It's how many, it's basically average. It's how many swats at the ball. I'm sorry, I'm not a golfer. It requires, in order to for a typical or a skilled golfer to get the ball in the hole. And so that is just an arbitrarily chosen point. It doesn't actually mean 0 swings. It means you have 0 more than somebody who's average at playing does. Okay, finally, a ratio scale of measurement is one better than an interval because it has a 0 point, an absolute 0 point. That means there's actually nothing of that thing. There are ordered categories, there's an equal interval between categories, but there's a 0 point. So some examples of this would be the number of correct answers on a test. You can get 12 answers correct, or 13 answers correct, or 14 answers correct, and each one more answer reflects 1 point higher. You can also score 0, which means you got none correct, a literal 0. The time taken to complete a task is another example. For instance, if you literally take 0 seconds in order to finish something, if it's completed as soon as the stopwatch starts, then that could be a literal no time. But you also can count from 1 second to 2 is the same as the distance between 3 and 4, and it's the same as the distance between 10 and 11. The gain in height since last year would be an example. You couldn't actually have height be a good example, because if you were 0, there's no such person as 0 inches tall, but you could measure how much higher you are this year than last year, and if you didn't grow at all, then you'd be a true 0 inches higher. So that that's an example of a ratio scale of measurement. I strongly encourage you to study and memorize those 4 words. Some people use N-O-I-R, Noir, to remember that. I'm not sure if you'll find that helpful, but you will hear that in future classes. If you continue to study statistics, you'll hear Noir as an acronym, as an abbreviation, to remember those 4 scales of measurement. I want to walk through some statistical notation next. Statistics uses operations and notation that you've already learned, but we also use a few more specific notations. Scores in statistics are referred to as X. It's Y, or sometimes other things too, but primarily we refer to scores as X. This is not a particular singular value like you might find in a high school algebra class, but this refers to all the values in a variable. I'll give you some examples of that later on. Capital italicized N is the number of scores in a population. A lowercase italicized n is the number of scores in a sample. Once you graduate from a statistics class, you might not find that capital and lowercase n's are always used in this way. Sometimes they use like a capital N just to mean sample, and sometimes they use it to mean like the large sample of a study, and they might have small n's to mean subsamples or subgroups of a study. But anyway, for the sake of this class, for most of our modules, we're going to use this notation. Capital N is the scores of a population. Lowercase n is the number of scores in a sample. Summation notation is required because many statistics make you add up a set of scores in order to compute the statistic. The summation sign, that's it's the Greek symbol for sigma, stands for summation. You can see it there on the screen, sigma. The sigma is followed by a symbol or equation that defines what is to be summed. So it might say like sigma x, and that would mean sum up your x. Summation is done after operations in parentheses and squaring and multiplication or division, but it's done before other addition or subtraction. Many of you are probably familiar with PEMDAS as an abbreviation that you learned in an algebra class. This stands for parentheses, exponents, multiplication and division, addition and subtraction. This represents, again, the order of operations that you're to follow when you're computing an algebraic expression. Summation falls between multiplication division and addition subtraction. It would be here. I want to go through an example of summation. Let's say that you ask your friends how many apples they've eaten this week, and you get the following scores. Again, in statistical notation, we're going to use x to refer to a variable. So person 1 got a 2, person 2 got 0, person 3 got 5, person 4 ate 3, and person 5 ate 2. So you've got these 5 people, each eating some number of apples. If we were to compute the sum of x, that would mean to add them all up. In other words, it would be 12. If you were to do the sum of x plus 2, following the order of operations rules, you can see that summation follows multiplication division, but precedes addition subtraction. So the sum of x means to sum them all up, and then addition subtraction would follow after that. So you would add 2 to the total of the sum of x. So add them all up, and then add 2. So that would be 12 plus 2, or 14. If you instead had parentheses around x plus 2, that would mean that you had to do the parenthetical expression first. So that would be to take each of the values of number of apples and add 2 to each score, and then sum them up after you'd added 2 to each score. So you could see how that would look. It would be to take each number of apples, to add 2 to each person's score, and then take the sum of those values, which would be 22. I have here some practice questions. Again, as I said before, I would love to be able to force you to do this. I can't, but I strongly encourage you to pause your video now and work through these examples. I'm going to show you the answers in a second, but please pause your video and work through these. Hopefully you did, and if you did, the answers are reflected here. The reason why I've given you this final expression here is not just to practice the particular computation that this is, but also because this form of computation will be used in virtually all statistics that you compute going forward through this class. And so it's really important that you understand the difference between the sum of x squared and the sum of x squared. The next section of this lecture is on frequency distribution tables. A frequency distribution is an organized tabulation showing the number of individuals located in each category on the scale of measurement. This can be either in a table or a graph form, but a frequency distribution always shows the categories that make up the scale and the frequency or number of individuals in each category. So as an example, you can see that some people will have we asked the question, what prompted you to visit our store? And some people will have been prompted by a newspaper ad, 1 person, a print ad, 2 people, a radio ad, 4 people, a TV ad, 2 people, because of banners, 2 people, and nobody said other. Those are reflected here in a graph as well. You can see 1 person said a newspaper ad, 2 people said a print ad, 4 people said it on the radio. These are frequency distributions, a table and a graph. It's important that we understand the basic structure of a frequency distribution table in a little more detail. Typically, the categories in a column are ordered from the highest to lowest, but it could be reversed. So you see here in this example, it goes from 5 down to 0. This is in the case of a numerical category. So if 5 is an option that somebody could get, then we could say how many people scored a 5. In this table, the frequency is 1. You could say how many people scored a 4. 2. We have 5 threes, 2 twos, 2 ones, and 1 0. If you want to figure out how many people were in your study or how many people are reflected in this table, you can add up the frequency because these represent number of people who scored various amounts. If you add these up, it comes to 13. So 13 people were reflected in this table. Now, if you want to compute the sum of the values, the sum of the original scores, you should convert the table back to original scores. So if you're to take this and write out the 1 5, the 4 2, the 2 4s, the 5 3s, the 2 2s, and the 2 1s, the 1 0, then you would write it like this. You'd write out all those individual scores. There are 13 of them, and then you could figure out what is the sum of all of these. We also need to understand the difference between the terms proportions and percentages. These are pretty intuitive words. You probably are already familiar with them, but a lot of people misuse the word proportion, so I want to articulate that for you here. Proportions measure the fraction of the total group that's associated with each score. So in this frequency distribution table, we have scores 5, 4, 3, 2, and 1, and we have the number of people who got each of those scores. The total number of people in this table is 10. If you add up 1 and 2 and 3 and 3 and 1, that's 10 people. If you take the one person who got a 5 and you divide that by the total 10, then you have a proportion of 0.1. If you take the 2 people who got 4s and divide them by 10, that's the total, then you have 0.2. That's the proportion. A percentage is different from a portion because it multiplies the proportion by 100 and puts it in percentage format. So if you take this 0.1 and you multiply it by 100, then you can write 10% as the percentage of people who got that score. 0.2 times 100, 20%, 30%, etc. These add to 100%. I want to also delve into frequency distribution graphs a little bit better. Frequency distribution histograms are pictures of the data organized in a graph. They require that you have numeric scores, either an interval or a ratio. It's okay if it doesn't have a real zero, you can still plot it in a histogram. It represents all the scores on the x-axis from the minimum to the maximum observed data value. But you have to include all of the values, even if somebody didn't score that score. In other words, if you have 0 people as the frequency of a value, you have to leave a space, a blank space for that value that nobody got. You also need to draw bars above each score that represent the corresponding frequency of how many people got that. Here's an example of a frequency distribution graph once more, but this specifically is a histogram because this falls on a continuum from 1 to 5, and each category here blends into the next category. So this runs from 1 to 2 to 3 to 4 to 5. These are not distinct and individual categories. It's on a continuum. One person got a 1, 2 people got a 2, 4 people got a 3, 3 people got a 4, 2 people got a 5. There are some general principles that we need to understand about all frequency distribution graphs. They always have 2 axes. The x-axis is typically the categories of measurement scale. It's usually increasing from left to right. The y-axis typically has frequencies increasing from bottom to top. And both axes should have a value 0 where they cross right here at the intersect. The height of the graph should be about 2/3 to 3/4 of the length. So in other words, it should be wider than it is tall. If you have a large gap in your data, then you should put a break in the axis. So like here, we have 0 at the intercept, but our data don't start until point 10. And so we put a little break here to represent that our graph doesn't start at 0, and we're not having a huge long line here before we get to 10. Also, we have another break here that represents that one person got a score of 100, even though most of the people got between 10 and 13. We put this break here to show that the line that we've abbreviated, we've cut out part of the line. It's really important that we understand how to use and misuse graphs. We never want to portray our data in a disingenuous way. These two graphs off to the right actually show the exact same data, but when you look at them, they show very different messages. So what's going on here? Take a moment and see if you can figure out. As you can see, on the y-axis here, we have misrepresented our jump from 0 to 42. There's no break in the axis here, but we've just zoomed in on this part of the scale. So it looks like the 08 year is twice what the 07 year was, and the 09 year is twice what the 08 year was, and the year 10 was a lot more than the year 9. But really, each of these points is just like 2 points or 3 points or 4 points higher than the last year. When we don't show the zoomed in graph and we just zoom out on all 4 years individually, you can see a more accurate representation of the number of homicides in this area. They are increasing, but not a dramatic amount like it looks in this first graph. So what principles might you follow in order to display data like this accurately? For one thing, you could make sure that you don't zoom in on the graph like this. And if you have to do something like that, make sure to put a break in your axis. Another example would be to not have a chart that's so much taller than it is wide. This second chart is wider than it is tall, which is an appropriate principle that we follow. Another type of histogram is called a block histogram. A histogram can be made into a block histogram by creating bars with individual blocks instead of tall bars that don't reflect the individual blocks. The reason why we do this is because each block represents one case. Therefore, block histograms show the frequency count in each bar. So if you have 3 people who got a 2, that's reflected by the 3 boxes stacked on top of each other. The reason why I'm going to use a block histogram often throughout the rest of this course is to remind us that each of these individual blocks is a case, is a person who got a particular score. And if we're to draw a sample from a population where all the scores are given, we might pick individual people who got a 4 or individual people who got a 2, but I might select from this group some of the boxes, and that will reflect that if I pick this box here, that's a person who got a 5. We also can draw frequency distribution polygons. In order to do this, we list all the numerical scores on the x-axis, like this, 1 through 7. We have to include any values, even if somebody didn't get that value. Like if there was a frequency of 0, we'd still leave a space there for them, and we would just make sure to plot the value at 0. And then you draw a dot above the center of each interval. So like the number of people who got a 6 was 1. The number of people who've got a 5 is a 2. So we put a 1 here above 6, 2 here above 5. And then once you've finished writing all your dots out, then you connect the dots with a line, and you close the polygon by bringing it back to the y-axis at 0. But it's important that we recognize this is really just the same thing what we've been doing all along. You can draw it in bar form or polygon form, and it's really the same thing. They're just different ways of portraying your frequency data. Now, everything what we just described was histogram data, where everything on the x-axis was on a continuum. Here I'm going to show you graphs for nominal or ordinal data. These kind of data are, again, categories. They're not on a continuum. They're not one blending into the next. So for non-numerical scores, like nominal and ordinal data, we use what's called a bar graph. It's very similar to a histogram, but there's spaces between the adjacent bars to indicate that this does not blend into this. These are discrete and separate categories, without usually some kind of particular order. Think back to the graph that I showed you before about how people heard about or were prompted to visit the store. A radio ad, a newspaper ad, banners, etc. Those were categories separate and distinct from each other, and they could be reordered in any particular order because one isn't higher or lower, better or worse than another. When we're drawing population distribution graphs, we might draw bars if the population is very small. Like our class is just about 25 students. The scores for each member in the class would then be used to make a histogram. So we could say these are the scores on exam 1. This is the number of people who got these scores here, 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 and here. But when a population is large, scores for each member are not always possible. We can't measure them all. And so instead of using bars to reflect a precise number of students who got each value, we might use graphs to we might use smooth curves to indicate that exact scores weren't measured in this population graph. So here you can see that the overall trend of the curve reflects the same as the overall trend of the curve above, but this curve is smoothed out to show that we don't know the exact number of individuals who got this high a score and this high score and this high and down here, but it's showing the overall pattern or the overall shape of the data. The next concept I want to talk through is normal distributions. If you measure a variable and plot each person on a histogram, it will often look like this. We call this shape a normal distribution. It follows this shape because most people are average. Some people are slightly above average, some people are slightly below average. A few people are very high, and a few people are very low. But most people are somewhere in the middle. Now, if we're talking about a big group of people whose scores have this basic shape, but we haven't actually measured each person, then we use a curve instead. This is called a normal curve, rather than a normal distribution. Well, that's not entirely true. A normal curve is an example of a normal distribution, but a normal distribution can also be reflected by a box histogram or any other kind of histogram. Here's an example of IQ population distribution shown as normal curve. Most people have an IQ of about 100. The standard deviation here is 15, so some people will get as low as 85 or 70, as high as 115 or 130, but you can see that most people bulk up around 100, a little higher, a little lower, but around 100. The normal curves are symmetric with the greatest frequency in the middle. This is a common structure in data for many variables. Some examples include height, weight, IQ, body temperature, hours slept, memory span, time watching TV, the amount of food eaten, hours worked, or walking speed. All kinds of things will reflect this overall trend of shape of graph. And the reason for each of these showing that is because most people are average on any of these categories, but some people are above average and some people below average, some people extremely above or extremely below average, just falling in the tails out here at either extreme end, but most people fall in the middle, somewhere around average. Most people are just typical on most traits. Researchers often describe a distribution's shape using words rather than drawing it, and so it's important that we understand the terms that they'll use in order to describe these distributions. A symmetrical distribution is one that's the same on either side of the middle. In other words, it's a mirror image of each other. If I drew a line down the center of this distribution, it would be the same on the left and the right. It's symmetrical. But it doesn't have to be normal in order to be symmetrical. This is called a bimodal distribution because it's got two modes. This kind of distribution falls mirror image around this center line here. It's the same on the left and the right. There's also this phrase called a skewed distribution that statisticians will use to refer to a distribution where the scores pile up on one side and kind of taper off in a tail on the other. If you have a tail on the right, that means you've got high scores that are positively skewing your data. It's these outliers on the outside that are causing your data to have a skew. If you have a tail on the left over here, then these low scores are skewing your data. They're the outliers. So remember, if you're trying to determine whether something has a positive skew or a negative skew, the tail tells. So this here has a right skew, this here has a left skew. Positive skew, negative skew. Now, in order to have a really good feel for the different types of distributions that exist in the world, I want you to work through this practice exercise, reading the descriptions of the different kinds of variables that we might measure in the real world, and the distributions that we might observe given that variable type. Please pause your video now, work through this, and we'll walk through it in a second together. Here are the answers for the exercise. The number of people born each month of the year is a uniform distribution for the most part. The same number of people are typically born in January, February, March, April, May, June, all the way to the end of the year. So we shouldn't see huge peaks or valleys. It's a uniform distribution. The GPA of students at CWU is likely to be negatively skewed because more people are going to get A's, B's, and C's than D's and F's. Only a few people are going to be very low here, but there's a cap up here at the A range. You can't have a normal distribution because nobody can get above an A. So you're going to have a bunch of A's, but nobody above an A. So it cuts off the possibility of higher scores of the distribution. The height of students at CWU is like this. You can see that the typical height of a person would be average. Some people will be taller, some people shorter, but most people will be average. Starting salaries of new graduates from CW will follow this distribution because most people will earn a relatively low amount of a uniform degree, but some people will luck into a really high-paying job right as they first start school, and so these people will be reflected here in the outer ends of the distribution where just a couple people will be making very high salaries, but most people will be making an average starting salary when they first start. Finally, the number of people eating at a steakhouse throughout the day might be bimodal, like you'd see a peak for lunch, and then around about 3 or 4 in the afternoon you'd see a valley, and then you'd see a peak again at dinner time when more people come through. So this might reflect like noon and 7 p.m., something like that. That's all I have to present for this module. I hope that you enjoyed and that it was useful to you. Please remember to do your homework, and we'll see you in a couple days for the next module.